All right, welcome back again for another episode of Con E 352 Mechanical Systems for Buildings. Today we're going to be talking about the refrigeration cycle. All right, the refrigeration cycle. Here's what I want you to do. I want you to grab the notes packet for the HVAC systems. We're going to look at page 3 is going to be the thing we focus on the most in here. All right. We've already talked about heating systems. Now we're going to move into cooling systems. So you need page 3. Also, there's going to be some PowerPoint slides on cooling equipment. You want to grab those as well. That'll be helpful to follow along with. All right, so let's go back to the refrigeration cycle. All right, little basics here. The refrigeration cycle is an engineering breakthrough. All right. Personally, right, there's like in terms of inventions that are important, there's the wheel, there's the refrigeration cycle, which gave us the ability to cool food and keep our buildings air conditioned. And then there's flight. All right. The refrigeration cycle developed right about the same time as the airplane was. And personally, I think it's more important. Of course, I'm biased and it's what I do for a living. So there you are. But still, the thing that was unusual about the refrigeration cycle, why it was an engineering breakthrough, and this is an important thing to understand. We are rejecting energy from a relatively warm space. I'm sorry, take that back. We are taking energy from a relatively cool space and we are rejecting it to a relatively warm space. Think about this for a second. We're causing heat to move in the wrong direction. All the calculations that we did, that's because heat is moving in the normal way. In other words, it wants to reach equilibrium. It wants everything to become balanced. If it's hot outside, cool inside, energy is going to flow from the outside to the inside. If it's hot inside and it's cold outside, like it's winter, energy is going to flow from warm to cool. Now, for heating, this is relatively easy to fix. It's warm inside and I want to keep it warm, so I'm going to burn something. I mean, essentially. Those are most of our choices for heating a building. We're going to set some fuel on fire. Whether it's coal, whether it's oil, whether it's natural gas, we're going to take it and we're going to burn it. And then that makes sense. We warm up the inside of the building and we lose energy to the outside over time. Now, in the summer when it's hot, this is a more difficult prospect because now I want the space to be cooler than the surroundings. I want to stay that way. I want it to reach equilibrium. But if energy is coming into the building and that's just normal because it's hot outside, how do I get rid of it? How do I get it back outside? That's where the refrigeration cycle comes in. And here's the engineering genius. It forces energy to go the wrong direction than it would normally. I'm removing energy from the building and I'm rejecting it to the outside. Look at the refrigerator. You want your milk, eggs, beer to be a nice, cool 35 degrees, let's say, just right above freezing, but not at freezing. I want it to be nice and cool. I've got to remove energy from that box, though. That box isn't going to stay that cool naturally. I've got to remove energy from that box and reject it to the environment. That environment is the kitchen. But I want my kitchen and the rest of the house to say it's 72 degrees. Let's say it's summer. It's 95 degrees outside. It's not going to stay 72 degrees by itself. I've got to remove the energy that is coming into the house, the sun, the heat transfer through the walls, the computer that's on, the people that are in the space. Those are all putting out energy. I want to remove that energy and dump it outside. Doesn't happen without work. At first, you think, wait a minute, I'm getting heat to be transferred the wrong way. Doesn't that violate some principle of thermodynamics somewhere? All right, isn't getting energy to flow the wrong way an aberration. It's a violation of the laws of thermodynamics. No, it's not. No, it's not. What we're doing is we are using work. If you remember from physics, our energy and heat balance equations, and bear with me, if you took physics at Iowa Western Community College, we'll try to go slow. Hold on. We are using work to force energy to be transferred. We are still obeying the law of thermodynamics. First law of thermodynamics, and I'm going to paraphrase because we need to understand both of these. You can't get something for nothing. If I want energy to be transferred, I've got to use work, and work is going to take other forms of energy to happen. What is that other form of energy? For air conditioning, it is electricity. We're going to consume electricity and make energy be transferred the other way. How do we do that? The refrigeration cycle, the vapor compression cycle. And that's the whole lecture today and Wednesdays and Thursdays lecture, maybe even once next week. All right. We're going to go over this a few times. In class, if we were meeting in person, I'm going to go over this no less than 3 times, or maybe 4 different days. For this class, we're going to go over it a couple of times, and you've got the ability to review it if there's something that you don't understand. So I'm going to try to give a pretty thorough explanation. And then for the equipment side, we're going to look at various types of equipment, from like the very, very small. Think like a through-the-wall air conditioner that you buy at Walmart, you bring it home, you put it in a window, you stick part of it out the back of the window, part of it's facing your room. There, air conditioning at its simplest form. At its most complicated form, we're going to find like a campus-wide system like we have at Iowa State, where you have some monstrous chillers. The basics of all of these systems are the same, and that's what we're going to go over today, the basics. So let's take a look. Let's turn to this simple diagram. We're going to go over the diagram first, how it works and its purpose of all the different pieces. And then we're going to go over pictures so that you can kind of see how does this fit into maybe a system that I already understand, like a residential system. So from the beginning, we're going to talk about residential systems because they're small. And then once we get that down, we're going to move up to larger and more complicated systems. All right, let's take a look here. Pull up page 3. We're going to start right here at the bottom with the compressor. The compressor, it takes a refrigerant, commonly thought of as Freon, but that's a product name. But a refrigerant, not water, not air, a refrigerant. It's a carbon-based chain. I'm not going to get into all the chemistry of it, but think Freon. It is going to take a low pressure, low temperature refrigerant in the gas form. Very important here. The inlet to the compressor is a gas at a low pressure and low temperature, and then it compresses it. Other examples of compressors: an air compressor, an engine, a gasoline or a diesel engine. All of those compress a gas mixture, and then while it happens, it heats up. So we take a low pressure, low temperature gas and we compress it, and at the outlet of the compressor, we have a high temperature, high pressure gas. To get it to do that, we have to use work. That's where most of the energy, most of the electricity that is consumed in this system, not all of it, but a lion's share of it is going to be consumed right here at the compressor. It is going to compress this gas, and afterwards it's at a high pressure. That makes sense. It's a compressor. But also notice that it is at a high temperature. And you might ask yourself, well, how did that happen? Because there's no heat transfer that's happening in this compressor. We're not getting any heat from anywhere else. This also isn't an engine. In other words, I didn't set anything on fire. I didn't add a spark to it to cause the components to combust. We just took this vapor, a refrigerant, a freon, and compressed it. It's at a higher pressure, and now it is also at a higher temperature. Why did this happen? All right, look in the center here. This equation, also known as the ideal gas law, PV equals nRT. I'm going to paraphrase. I'm going to assume that you already understand the ideal gas law, but just as a refresher, pressure and volume is equal to a constant for that particular substance times R times T. Our point here is that if all those other things are constant, if the pressure of a substance is increased, the temperature of that gas is increased as well. And by substance, I mean a gas. If I increase the pressure on something, that something gets very, very hot. Increases in temperature. We use this in a diesel engine to set the fuel mixture on fire. There isn't a spark plug in a diesel engine. Just the act of compressing the air and fuel mixture gets it hot enough to combust. We're not combusting anything here in our particular compressor, but we are compressing that. We're compressing that gas to get it hot. How hot, mind you? Well, how hot we get it depends on where we're trying to reject energy to, because in this next item is a heat exchanger. This is the condenser. This is where we reject heat out of the system. On a residential piece of equipment, this would be the part that sits outside. We blow air across it. That's this 95 degrees. This is the outside air, just the ambient air. Wherever this condenser is sitting, we're going to blow air across it. There's a whole bunch of coils, big copper coils in this. We've got the hot refrigerant vapor on one side of the coil. We've got the ambient air from the outside blowing across it. We compress this gas until it is hot enough to reject heat to the outside. How hot? Doesn't matter. It just has to be hotter than the ambient air. Notice we're going to reject heat to the ambient. In other words, if I blow air across this, it gets hotter. It took some energy with it. Where is it taking that energy? What made the ambient air warmer? The hot vapor that's in the refrigeration cycle loses energy to the ambient air, and now it condenses. Just a note, the terms for the refrigeration cycle are fairly self-explanatory. There's no tricks. The compressor, it compresses the gas. The condenser, it condenses that refrigerant from a gas. And then at the outlet of this, we have a slightly cooler, it's still hot, but a slightly cooler, still at a high pressure, but now it is a liquid. We've condensed it. We've exchanged energy with the outside environment. That vapor has lost energy, and now it is condensed down to a liquid. We have taken advantage of the phase change. Remember how the reason steam can transmit a whole bunch of energy is that the energy we put into it to boil it causes a large amount of heat transfer. Per pound of water, turning it to steam is a lot of heat transfer. And then when we use steam, like at a coil, a radiator, wherever that is, it condenses back to water, and it gives that energy up to whatever it is we're wanting to heat. Well, same thing's happening here. In other words, this vapor, when it condenses in the condenser, gives a lot of energy. Per pound of refrigerant, it gives up a lot of energy. And now, on the outlet of this, it is a liquid. A slightly cooler liquid, but a liquid, still at a high pressure. The next item, the thermal expansion valve. I want you to think of this thermal expansion valve. Its sole purpose is to cause a change in pressure. This high pressure liquid coming in here hits the thermal expansion valve. Also, think of the thermal expansion valve as some type of a gatekeeper, an orifice that only allows as much refrigerant past it as is necessary. How much refrigerant gets past it? Well, it depends on the demand. How much cooling effect do we need? When this refrigerant hits the thermal expansion valve, it releases that liquid refrigerant, but it releases it at a much lower downstream pressure. This pipe is larger compared to this pipe. And this pipe is directly attached to this evaporator coil. That's the next item in our list. So when it leaves the thermal expansion valve, it is at a low temperature and a low pressure liquid. It's not completely liquid. Most likely it'll start when you drop the pressure on a liquid. What happens is you start to get vapor forming again. We lower the pressure. It's still hot. It allows a vapor to form. And then it hits the evaporator. Think of the evaporator as a big open space where this vapor can boil off and expand. What happens when a gas expands? If everything else stays constant, as that gas expands, it gets cold. Anyone who has discharged a CO2 fire extinguisher knows what happens to the nozzle. You discharge it, and the tip of it gets really, really cold. What is happening? That gas is expanding. If you've ever played paintball, you've had a tank of CO2. As you use it, that tank pressure goes down. That CO2 expands as you let some of that CO2 out. The tank gets cold, maybe even frosts a little bit. On a natural gas, like if you have a propane grill, if you got a tank of propane, and let's say that you're having a great barbecue and you're using a ton of this gas, notice that that tank might start to condense or it might start to frost even. As that vapor that's held in that tank expands, it'll get cold. That's what's happening in the evaporator. We have changed the pressure on the refrigerant here. It expands, especially when it hits the evaporator coil here. It expands and it gets cold. Notice what's on the other side of this heat exchanger. The evaporator is a big heat exchanger, but now it's removing energy, and it's removing energy from the return air. Think like our air handler at our coils. That's where the evaporator coil is. We've got return air coming back from a space. We put it through the evaporator, and now it's supply air. It has been conditioned, and it is 55 degrees. The ideal gas law that caused this vapor to get hot when we compress it works in reverse here. Ideal gas law strikes again here. And as that evaporator allows that vapor to expand, the coil gets cold. We hit it with return air. That return air is relatively warm, and we cool it down to supply air temperature. Now it's 55 degrees, or at least that's right about where we want it to be. And it gets turned into supply air, and we use a fan to blow that supply air into the room for air conditioning. A low temperature, low pressure gas leaves here. It has more energy than it had here, but then it hits the compressor. The compressor compresses it, and the whole process starts over again. And it just goes round and round and round and round. The compressor does most of the work. It compresses the fluid and it pushes it around in this circle. An increase in pressure happens here. A decrease in pressure happens here. Energy out of the building and out of the system happens here. We reject it to the ambient environment outside. Energy into the system happens here. We are removing it from our space, our people space, the space that we want to stay cool. We remove it here. We reject it to the outside here. And this goes around and around and around in a circle. All right, there's a little diagram here that I want you to... Basically, I've taken, instead of the pictures, we've just changed this to a little bit of a simplification. Compressor has a pressure change. The thermal expansion valve has a pressure change. This side of this line is the high pressure side. This side of the line is the low pressure side. Below this line is the vapor. Above this line is the liquid. Only one change happens at any piece of equipment. We have a change in pressure. We have a change in phase. And we get heat transfer here. We have a change in pressure. We have a change in phase. And this is where heat transfer occurs. As long as you keep those parts simplified, you understand the purpose of each of the individual parts, it's easy to keep straight. How much do we need to compress it? Well, until it gets hot enough to reject heat. And maybe that's outside. Maybe it's to another water stream, whatever it is. But it's got to be hot enough to reject heat somewhere. How much does this expand? Well, how cold does it have to be? How cold does this coil have to be? Well, we don't just remove sensible energy from this return airstream. We also remove latent energy. This coil has to be colder than the dew point. Important point here, right? Write this down. The temperature of the evaporator coil has to be at or below the desired dew point temperature that we want in the space, in the room, in the building, in the people space. Because, notice this drip pan, as this return air hits that coil, it's going to condense some of that moisture. And what that drip pan does is it catches that moisture as it falls off the evaporator and then takes it to a floor drain. All right, let's switch over to the PowerPoint slides because I want to take a look at some pictures that this represents. Right? Now, before we get to the actual equipment, let's see where cooling started. The icebox. The icebox was truly a box where I put ice in it. See, once again, no tricks here in our terminology. And yes, if you've ever seen the opening to Frozen, that's what they used to do. They used to go to a lake where it's cold and see the guys there. They are harvesting ice off the lake. They are cutting it with saws. See these blocks that are sitting here? They're going to cut that into nice little blocks that fit in here and then sell it to people for cooling, because prior to the refrigeration cycle, that was the only way to store food and to keep it cool. They would take these blocks of ice and bury them underground in an ice house. Ice house would just be a big insulated building, probably with a very, very, very deep basement to it. They would bury the ice in sawdust, pack it in there. And yes, over time, some of it would melt. But if you packed enough ice into a big enough area and insulate it really, really well, you might be able to sell ice all summer to people who wanted to keep their drinks cool. So at first, this was the way that you kept milk, food, other perishables cool, is just blocks of ice. So guys would go around in horse carts selling ice. Here, let's enlarge this just a little bit. So they go around during the day. These guys that are sitting here harvesting ice all winter, They store it, and then they're going to turn around and sell it all summer. This is where we get the term 1 ton of cooling. When you go to buy a refrigeration system, usually the capacity is listed in tons. That is a 1 ton window air conditioner. That is a 5 ton residential air conditioner. Oh, look at that rooftop air handler that has a 100 ton capacity. Or if we go down to the physical plant for Iowa State, you'll see chillers that have a 1,000 ton capacity or a 3,000 ton capacity. The ton does not refer to the weight of the equipment. A ton refers to 12,000 BTU per hour of cooling capacity, which just happens to be the same cooling capacity that you get when you melt 2,000 pounds of ice in 1 hour. Yes, that's what that means. In class, this is where students stare at me and they're like, you made that up. That can't be a real thing. Yes, it's a real thing. It's a real thing. This is how we size air conditioning systems. Hey, that's a 4 ton. That's a 5 ton unit. It's the amount of ice melting in an hour. Think about this for a second. A large building the size of Town Engineering may very well have a 300 or 400 ton chiller on it. Every hour, that's the same heat transfer as 300 tons of ice melting. Valley High School, as an example, had a single 1,000 ton chiller in it to provide cooling capacity for the whole high school. If you were to try to do that, that would be a whole lot of tired horses and horse carts. Who can we thank for this marvelous invention? Willis Carrier invented air conditioning in 1902. Let us pause for a moment and give thanks to the amazing invention that is air conditioning. Like I said, there's the wheel, there's air conditioning, and then there's flight. I don't care what they say in the aerospace engineering department. This is more important. All right, moving on. Let's look at some pictures. Check out some equipment. This is a picture, a drawing of a residential system. Kind of shows it all at once. The outside part, the condenser, and inside the condenser is where they're going to put the compressor. It's all together, all in one. There's going to be some refrigerant lines that go over to this part. We already talked about the furnace section. The ductwork is going to be, and the furnace with the fan, those are all going to be used. Same ductwork system on a residential. It's just that we bolt an evaporator to the top of the furnace. Now, some of the other things in this particular drawing that you probably won't have to worry about. All right. This item 9 is an outdoor air heat exchanger. If we wanted to bring in some outdoor air and exhaust some of the outside and exchange that energy, in other words, recover that energy, you can get one for a residential piece of equipment. That's what number 9 is. Number 8 could be like a higher efficiency filter, or maybe even electrostatic filter. I'm not a terribly big fan of them, but we are going to talk about filters later in part 2 of this class that we're in. Let's see here. This unit outside is an emergency generator. Here in Ames, we just found out why it may not be a bad idea to have an emergency standby generator at your house. Right, so those are the basic parts. We're going to take a couple little close-up looks. The furnace we already looked at. We're going to bolt that evaporator section to the top of it, and then the heating section is off when we're air conditioning, and we're just using the fan that is located in the furnace to circulate the return air and then turn it into supply air. The outside unit, the part that you see outside, that is the condenser, and inside of it is a compressor. For a residential unit, it's really just a big black cylinder perhaps, or a black box that has a small compressor. Now, if you want to learn how compressors work, there's mechanical engineering classes for that. We're not going to get into it. In this class, I just want you to know that that's what it's doing. It is compressing the refrigerant. It is physically located, in this case, inside of the evaporator coils. Take a look at this picture. You'll see this cutaway view. It's a bunch of copper tubes. That's where the hot gas goes to condense. See the fan on the top? That is pulling ambient air through this coil and then up and out. If you go to a residential unit, put your hand over the top of it, that air will be much warmer than the ambient air. It'll probably be 115 degrees or so, right? So that's where it's rejecting heat. Wherever this is located, it needs to have clear airflow through it, unobstructed airflow, because this is where we are rejecting heat to the ambient environment, to the outside. A lot of the refrigerant pipe, and I want to say the thermal expansion valve is also located inside of this. All right? Ooh, no. The thermal expansion valve a lot of times will be on the evaporator coil. That's the next picture. Here we go. Here's the evaporator coil. Here's a picture of one. Here's our furnace. It's just going to sit on top of it. Here's the evaporator coil. You can kind of see right there. The evaporator coil is going to have the thermal expansion valve inside of it. Now, you're not going to see this. This is just going to be covered by a big piece of sheet metal. That's what that metal covering is right beside it. And then inside, here is a picture of a thermal expansion valve. It's just going to be a brass control valve with copper fittings. See this copper wire in that bulb? That's going to be actually placed on the in the coil itself, or in the airstream itself. It'll measure the temperature of that supply air. It wants to keep it at 55 degrees. If it's too warm, this valve will open up and allow more refrigerant through and increase the cooling capacity. Too cold, it'll shut this valve down. It'll restrict the airflow of, see this from condenser, this hot, or I should say this liquid that's coming back, high pressure in, low pressure out. It'll let this liquid out, and as it gets to the as it goes through the evaporator section, it'll all end up as a superheated vapor on the outlet. On the inlet, it's liquid, or mostly liquid, at a low pressure. As it expands, as it goes through that evaporator, it heats up and then it expands. That expansion is what causes this coil to be cold, and then it goes to the compressor and we go round and round and round again. All right, I'm going to get into other than the residential systems for next time. All right, back to our lecture notes. Okay, so let's recap here. Most of the energy consumed by this process is consumed in the compressor. The compressor causes the increase in pressure from the low pressure side to the high pressure side. This has to be a gas, a vapor coming into it. Note, if any liquid refrigerant was to leave the evaporator, that would be a very bad thing, because, hopefully, once again, physics kind of subject, if a liquid gets to the compressor, the liquid cannot be compressed, although the compressor will try, which means it could easily damage the compressor, cause a bunch of damage. As the compressor tries to compress a liquid, it's basically just like hitting it with a sledgehammer. Internally, it has controls that should shut it down if that happens, but it can still damage it. So we want this to be a low pressure gas coming into the compressor. It's where we use a lot of our electricity. This is where the work input is for the system. Turn it to a high pressure, high temperature gas. head to the condenser. Condenser is a heat exchanger. Important thing, on both of these heat exchangers, the refrigerant does not touch the air. It's a heat exchanger in which the two fluids never physically touch. They are always separated by something, and that is the walls of the coil itself. So it goes through there. We condense that vapor to a liquid, still at a high pressure, still fairly warm, and it goes to the thermal expansion valve. At the thermal expansion valve, we have a change in pressure. It's a low pressure leaving. It is a liquid, but it is at such a low pressure, we start to get vapor coming off of it, and then when it hits the evaporator, it gives a big space to evaporate. That vapor expands and gets cold. The evaporator is a heat exchanger, so it blows return air over that coil, exchanges energy with the refrigerant. It boils that refrigerant, or rather, the refrigerant evaporates. The air gets colder. The refrigerant gains energy. It is now a low pressure and low temperature gas, but still has a higher energy state than up there. Not only does that return air lose temperature, loses sensible energy, it also loses latent energy in the form of moisture that condenses on the outside of the evaporator coil. That coil, as it drips, we have a drain pan that directs that water away. All right. Couple of thoughts here. One important thing to notice. The first law of thermodynamics is you can't get something for nothing. In other words, I can't get heat transfer without consuming some energy, work. I can't get something for nothing. I can't even break even. That's the second law of thermodynamics. And yes, I'm paraphrasing here. All right. Paraphrasing. Second law of thermodynamics. I can't get something for nothing. In other words, there is resistance and friction within this system. The energy that I pull out of this side, I have to reject here at the condenser. But I also have to reject even more energy at the condenser because of this friction. So the energy transferred outside here is greater than the energy input here, and that difference is the amount of energy put in here by the compressor. Ultimately, all of the energy in the compressor gets turned into friction somewhere. And that heat has to be rejected at the condenser. This is why you can't get something for nothing. We have to reject more heat than we take, and that is because of the compressor energy. All right, let's pause there so I can get this put up into uploaded. Right, 1 ton of cooling still right here. Don't forget what the 1 ton is. Think of the guy selling ice and the horse carts. All right, I have some other diagrams here. All these different diagrams that I have, they show the same thing. They are just graphically slightly different. This one is an image that I got online, and it just has the compressor here and shows the energy going the other, just the cycle going clockwise instead of counterclockwise like I showed. I just have different diagrams because you might see it in different ways in different locations. I just want you to know that they're all the exact same. All right, when we come back, we are going to look at different options for different pieces of equipment depending on the total size and capacity and needs of your building. So study this, and we'll come back to you later.